I told you I would show you some demos. So here they are. The first thing I'm going to start off with this it's called AR kit. I think it's augmented reality. I don't really know what it is. But there's, and if your phone, you can do a whole bunch of awesome things. So one of the awesome things, and I haven't used this in a while, is this measuring app. So you can like use your phone and move around the camera and you can actually measure things. It's kind of cool. How does it work? It deals with some stuff that we don't absolutely talk about, but it leads into something else I'm going to show you. So if you haven't seen that before, it's built into, I think it's built into iOS now, and I'm sure the Android has something like this too. Number one thing, this is me, I want to show you one of the things that we talk about is parallax. Parallax is important. You can do this demo yourself by just looking through one eye and then looking through another eye and looking at something like your thumb. And when you do that, the thumb appears to shift with respect to the background. Okay, so how does that work? Well, here are two cards, and you'll notice that as I move the camera, one card, the card that's closer to me, appears to move more than the card that's farther away. And so this is the result of what we call parallax, changing your observation position and viewing things that shift in their position. Let me show you a diagram. It's super important in astronomy. We're not going to get into all those details, although we could. We're just not going to. Imagine that I'm at point A right here, and I'm looking at these two objects, and they're in a line. But then if I shift over here to point B, then I can see that the relative position shifts. And in fact, if you know the distance to the object and the shift amount, you can find the shift angle. You can find out how much they shift. So I'm not going to go through the math of that, but you can. The closer it is to you, the more its apparent shift is going to be. Okay, so this is one of the things that your camera does to determine how far away things are in order to measure it. There's a couple other pieces too. But how does it know, how does your camera know a different viewing position if it only has one camera? Yes, you have more than one camera on your phone. I get it. Most of them do. But it's only using one at a time usually. So here's one of the ways that you can measure the shift. Suppose that you know your initial position and then you move. You have to accelerate to some speed and then have a negative acceleration to stop. So if you know the acceleration and how long the acceleration was for, you can find the change in position. This is from kinematics. You took this course, right? This is a course before this course. So the point is that you can determine the distance if you know the acceleration, but how do you know the acceleration? Well, here's one way. This is basically what your phone does with its accelerometer. So here I have a mass on a cart and another cart, and they're connected by rubber bands. And when I pull it, watch what happens to the rubber band. The rubber band stretches. Okay, so if you can measure the stretch of that rubber band, you're essentially measuring, and you know the mass of the cart, you can essentially measure the acceleration. And that's what, it's kind of more complicated, but that's basically what your cart does. So that acceleration is important so you can measure the change in position. Now, what about the angular size? Because here's two cards that are actually not the same size, but they appear the same size. So we have this thing called angular size and actual size. And you'll see here it was a trick. I tricked you all along. The blue square is smaller. And this is you could call this a perspective trick. I'm fine with that. This is how they make Hagrid look really big in not Lord of the Rings, Harry Potter, and they make the hobbits look really small and the dwarves in Lord of the Rings and the Hobbit by just putting them closer or further away from the camera. It's a pretty cool trick. Okay. So we can measure angular size if you know the angle that it appears at and the distance to that object, then you can measure the length. Or vice versa. If you know the length, you can measure the distance to it. But with the camera, normally what we're doing, you're measuring the angle, right? Because you are using, you want to find the length. So you use parallax to find out how far away it is, and then it uses the angle to find out the size of it. And that's how ARKit measures those things. This is something that's even cooler. This is LiDAR on the iPhone. I scanned part of the building by walking around and looking at different things with my phone, and it has a LiDAR array that shoots out an infrared beam and times how long those beams take to come back and determine a distance that way. And it's just amazing what you can create with this kind of stuff just with your phone. Kind of cool. Here's another picture just for fun. This is in downtown Hammond. They have this sign here, and I walked around and scanned it, and then I have a 3D model of it in my phone, which is kind of cool. I could 3D print it or something like that. That'd be cool. Okay. And that's not really related to the stuff, but this is refraction. Let's go over some examples of refraction. Here is one that you may have seen. When the sun sets, it looks kind of weird. And that's because, remember, refraction happens when light enters one medium to another with a different speed. And that's what that index of refraction represents, the relative speed of light compared to that speed in the medium. So we live on Earth, and we have this thing called an atmosphere, and the speed of light in the atmosphere is slower than space. So when light comes in, it's going to bend. Now, this is an exaggerated view, but here we have the sun where it actually is. Here's where the sun actually is. When the light comes in, it bends down. Our eyes perceive it to be over there. Now, how do you get a weird sun like that? Well, the top of the sun is at a different location at the bottom of the sun, so it's going to enter at a different angle. So they have different amounts of refraction from the top and the bottom of the sun, and that's what causes this interesting thing. But maybe this one's more cool. Here is a picture of a person. I can't even tell if it's a kid or an adult, in a pool with a glass wall, and it looks like the person's head is not connected to the person. And so this is a funny picture from a football game, bowl game. Wake Forest is winning. And here's one that I reproduced the same situation with a Lego figure, a minifig. So there's a minifig in a water, and I'm looking at it from the side with a glass wall. And so if you just look at the part of the body in the water, that part of the body, the light comes off of that. When it leaves the water and comes into the air, it refracts and bends. So then the camera or the viewer traces that back and shows that image over there. Now for the head part, it does not go through the water. So you have different locations for the actual image for the body and the head because one's going through water. It's kind of fun. Here's another cool application of refraction. This is called Snell's window. So the idea is, let me go to this picture right here. So imagine that light, and we can draw these arrows either way. So if light comes straight down, it goes straight into here. This is water. If light comes over here, it refracts down and bends that way. If light comes off, it reflects that way. Now, what happens when light comes at the critical angle, and so that the angle of refraction is equal to 90 degrees, then the light doesn't actually leave the water. It will come up here and just go that way. And the same thing's true if light came this way, it would come down there. Now, what if the angle's greater than that? Well, what if I have a light coming up here? It's not going to leave, it's going to only reflect. So you can't see out of the water beyond this little cone of visibility. Okay, and it's due to refraction of the water and total internal reflection. So right here, this is a great picture. One of my friends posted this online, and this is in a pool looking up, and there's a little figure there. Notice this circular part. You can see the roof of the indoor pool. But over here, beyond that, what are you looking at right here? I love this picture because you're looking at the bottom of the pool. This is reflected, totally internally reflected light from the bottom of the pool that reflects down to the camera. So you can only see out through this window. This is a picture, this is actually my wife in the Bahamas, and it's not quite as good of a picture in terms of Snell's Law. It's actually a great picture. One of my friends took it. But you can see that over here when it gets really dark on the edges, that's because you're looking back down at the bottom of the ocean, and it's pretty deep here, so it's much darker than that other part, so it doesn't really get exposed. You can't clearly see the window like you can here. Look at that. Look at that nice circle. Very nice circle. Okay. Here's another example of total internal reflection. These are fiber optics. This is actually a fiber optic bundle that's called scintillating fiber optics. And what they do is when a charged particle enters the side of it, it produces light. And that light, since the index of refraction is very high for these fibers, gets totally internally reflected, so it only travels down to the ends. So these ends look brighter than everything else because light's coming in from the side but leaving on the ends. This is used for a particle detector, and when a charged particle comes in, it produces light, and that light travels down to the ends, and you can detect it and measure things like that. This is an experiment that I worked on in Fermilab. It broke, so I took this bundle. Don't tell anyone, but I still have it. Okay, what about reflection? Let me show you some cool stuff with reflection. Here is a picture showing normal reflection with a mirror, and this is not an easy picture to take, okay? And I made this picture, but it's not easy. So I have two laser pointers, and they're at two different angles, and they reflect at two different angles. So this one comes in, angle of incidence, angle of reflection. This one comes in, angle of incidence, angle of reflection. That's what you expect, and that's what we have right here. That's your normal law of reflection. This is what happens when it hits a non-shiny surface. So notice, especially with the green laser pointer, it comes here, it hits the white paper, and then it reflects in many directions, and essentially all directions. The red does it too, but you can't really see it because the green's so much more. I think the camera is more sensitive to the green, but we get light reflecting in all directions. One place where you might see this is if you have a flashlight or the headlights on your car, and you're at the nighttime on a dry road, the light from that headlight hits the road and it scatters in all directions. It's not shiny. It's a not shiny road, and some of that light comes back to your eyes, and you can see the road. If it's a wet road at night, it's actually very difficult to see the road, because what happens is light from the headlight comes down, and it's a shiny surface, so it just reflects in one direction this way. Since no light's getting back into your eye, you don't see it. It's just completely black. You don't see the road. That's what makes it hard to drive at night on a wet road, unless you have some help from something like this, a retroreflector. So here is, unfortunately, I was driving. This is the same night, okay? They were renovating one of the interstates, and they were adding in the retroreflectors. So there was a portion of the road that did not have retroreflectors and the one that did. So this is just plain white painted lines, and you can see that I can see one line, two line, and then I really can't see those other ones up there. It's really hard to see them because the same thing happens. Light comes down from my headlights. Most of it reflects away, and some of it reflects back, but not very much. However, if you add these retroreflectors, these little block things to the white lines, you'll notice that you can see them much greater. So a retroreflector reflects light not in the same angle, but back to the observer. And so that allows you to see them. Here is a very, very simple retroreflector. It is a corner of a cube with three mirrors. You only need two in 2 dimensions. But notice that this laser pointer comes down here, and I'm using laser with fog so you can see the beam. And then it bounces off that one at an angle of incidence is angle of reflection. It bounces off that one, and then it comes back. So it comes back in the same direction. So it doesn't matter. The red one does the same thing. It comes at that same place from another angle, and it bounces there and comes back. So pretty much any angle that you shoot this laser at, it's going to come back to the way it started from. So it reflects it back to its own direction. That's why it's called a retroreflector. Here is a radar retroreflector. I want to show you that they're real things. These are small devices that you could put on your kayak if you're out in the large lake or in the ocean. And what it does is it reflects radar very well back to where it came from. So if a boat has a radar, your kayak gives a bigger radar reflection signal than if it didn't have that. So it's more likely that they'll see you and hopefully not run over you, because that's just called bad. Here is another retroreflector. This is on a bike. So a bike and a lot of signs, a lot of traffic signs have retroreflectors that are not squares like that. They're not cubes, corners of a cube. Instead, they're tiny glass beads. These are actually pretty large glass beads. So it turns out that a sphere of glass can act as a retroreflector. Here's a tube with oil in it, and you can see this red laser comes and hits it and comes back. The green laser at a different angle comes and hits it and comes back the same way too. So they'll act like that. So if you look at, here's another example of a glass or spherical retroreflector. This is a great picture. I took this picture too. I have 2 dogs. We have 2 dogs, and isn't that great? So you can see their eyes, because if you hold the flashlight near the camera, the light comes and hits their eyes and bounces back. Their eyes act like retroreflectors, so they show up as eyes in the dark night. This would happen. This is a common way for cartoons to show eyes, to just the glowing eyes. Because imagine that you're at a fire in the woods at night, and your back is to the fire and you look out at the animals. Well, now the same thing's true. The light's coming from the same location as your eyes, reflecting back, and you can see these eye things. It's kind of cool. So we see retroreflectors everywhere. They're on your shoes. They're very, very tiny, small beads, and they make it so that light reflects back in the direction that it came, and it makes it much more visible. Pinholes. So this is not part of the chapter, but it does a lot of the same things. So a pinhole is really just a super tiny hole, and when light comes through, light source over here comes through that hole, it's only going to be able to go through one way, and it's going to leave a little spot down here. And here is what happens if you have two lights with the pinhole. So here I have a pinhole right there. I have an orange or red light and a green light on the stick. And you'll notice on the screen behind there, I get a green light and a red light. So in this, well, I guess it's orange. I don't know if it's orange or red. But in this case, you'll notice that the orange light and the green light flip directions because of the way the light travels. Light can only travel through that hole up here, so you get the green spot up here, the orange spot down there. If you have two holes, each light's going to make two spots. Okay, so you can get more complicated with this stuff. I'm not going to get into it, even though I did include a picture right here. But the main point is, this is actually an image of this. If I have this whole thing filled in with lights in between, they'll appear upside down. So you can form an image on a screen with the pinhole. It's not as good as a lens because you have a very, very, very tiny amount of light that can get to that pinhole, so the image is very faint. It's better than a lens because there's no focal length. It doesn't matter how far away you are, it's going to make an image on that thing. You don't have to be at the right location in order to form an image. Here is a pinhole image. This is images of the sun during a solar eclipse. So the leaves in a tree form tiny little spaces, and those act like pinholes. When the sun sunlight comes through there, you get an image of the sun on the ground. So these are all different holes in the leaves or between the leaves, and you get pinhole images of the eclipsed sun. So you can see here it's about 90% eclipsed. If you didn't get to see a solar eclipse, I don't know what to tell you, but you missed out because it's super awesome. You got to be in the next time you get a chance. Total solar eclipse. Total. 90% is not good enough. Total. You got to get the total. This is a pinhole camera. I don't have a really good picture of it, but the idea is right there is a tiny little hole, and I can cast an image on the screen. But it's super dim image, so you have to have it super dark. I sealed up the box and put a phone in there to look at the image. It didn't turn out perfectly, but you can build bigger boxes and stick your head in there, and you can actually see the images. It's pretty cool. Here is a camera obscura. And in this case, we have a hole in the wall right there, and in this room over here, that hole casts an image inside this room. What does camera obscura mean? It means room. Think about your Spanish or Latin or Italian. Dark. It means dark room. So a camera is a room. Okay. And so this is a room with a tiny hole in it that casts an image. Now, what do you want to do with that? Well, you could trace over the image and do a whole bunch of cool art stuff, and that would be cool. So a pinhole can cast an image too. Okay, that's enough extra stuff. Told you I'd show you some extra stuff. I showed you some extra stuff. I hope you're happy. That was fun. There's a bunch of other cool stuff, but you got to make connections, right? You can't just calculate the focal length of a lens and, calculate Snell's law and all that stuff. You got to see it in real life too, because the real life is awesome. The end.